Hello everyone, welcome back to ECE350, lecture 9, part 2. In the last lecture, we showed you that you can match the load with the characteristic impedance of the line to minimize the reflection from the load, all right? And that happens with what we did last time, we basically add a reactive part, either inductor or capacitor at this point over here, distance d, from the load to match it. So if you look at from here now to that way, your y in would be equal to y0. That means you perfectly matched, right? And also you know that few class back we discussed that your short circuit step or open circuit step, that there could be either inductive or capacitive based on their length. So look at here, this is open circuit step. For the first 0 to quarter wavelength, they're capacitive, then they're inductive and alternating. And this one here, short circuit step, that is first quarter length of the length, quarter wavelength is inductive, then capacitive, then this goes back and forth. And that's because of these two equations here we discussed in previous chapters, right? So now, can we use, instead of, you know that this short circuit one, or if we have an open circuit one here, line, there could be either capacitor or inductor. So if we have a very high frequency, this line length could be small length and smaller than your actual part. So then we can use short circuit step or open circuit step to do the matching instead of real capacitor inductor, right? So how do you do that? There's the next over here. So we're gonna continue the last. Problem we did. So let's go back here. So this is the same problem we did last time. Before I go anywhere, you know that when we first discussed the Smith chart, at this point over here, at this point over here, both RL and XL0, right? So that means this point is called short circuit impedance. So this is the short circuit impedance point, right? And this point over here, at this on the other side of this point over here, RL and XL both are infinity. Then this is called this point over here is called open circuit impedance point, right? So now you know that if you go from one side to another side, you get the admittance, right? So if this is the short circuit impedance here, then on the other side we have short circuit admittance. Can you see that? And if this point is open circuit impedance here, on this side over here, you'll get open circuit admittance. Right? So remember that. So in matching, we only work with the admittance. We don't work with the impedance. So I have to be careful about this guy over here, short circuit admittance, and also need to be careful about this one here, open circuit admittance. We forget about the impedance now, okay? So now, from the last problem, we had 2 points. So we have point over here, and we have point over here, right? 2 points, right? So at this point over here, my y d1 is, or bd1 is positive j1.58. So that means my bs1, jbs1 would be negative, right? So I need this. I need this impedance to match. So I have to find that on my admittance. In my Smith chart, I have to find this value. So if I do this over here, if you look carefully here, this point over here represent y as equal to negative j1.58. So this is the negative part of your admittance. So that's right here, right? So that's the value negative j1. What I'm saying that if you can see very closely 1.4 here, then 1.6 here, the point is negative 1.58. So now what's going on here? So you know that this is my short circuit admittance step, right? Short circuit admittance step. So that's the starting point. I have to work from here to here. I have to work from here to here to find my this point. So how much I need to work? There is a distance d1. That is the distance d1 I need to know, right? So So that is the, so I have a short circuit admittance over here. Then if I go from that's let me from here. So what I'm doing here, I have, let me put a graphical node over here. So at this point I need to use a short circuit step, right? So I'm trying to find this length over here, how much length I need, how much then length I need to find the admittance of negative negative j 1.58. So this is the length I'm looking for right now. Okay, so that length is basically from short circuit admittance stuff. From there, how much length I have to, that's right here, that's L equal to 0.09 lambda. So that means my length over here, this length over here is 0.09 lambda. So if I have that much long short circuit step, that will give me 0. Negative j 1.58 admittance in normalized value, right? That's what it's saying. Okay, so now if we use this point over here, if you want to use this point over here, so that that point, your value will come positive 1.58. So that positive value you need to find it somewhere else over here. Let's find it 1.5 positive 1. It would be somewhere, let me see, maybe next page. So let's see, that would be 1 point, yeah, right here, should be somewhere here, right? Somewhere here. So I'm going to try to do that. So that is somewhere there, right? So now I have to go from here to that point. So I have to come from here. It's a still short circuit I'm using. So I have to go from here to all the way to this point over here. So this point, what is the value on this point over here? I'm working, so it's 0.16 lambda at this point, right? Then I have to work, plus I have to work 0.5 from here to here is 0.5 here. So that would be L2. For my L2 would be 0.25 plus 0.16 lambda is 0.41 lambda. So if I use the this matching point over here, my short circuit step need to be further longer. So it need to be further longer here. That length would be L2 would be 0.41 lambda, right? So that's how you use the short circuit step. Now if you want to use this open circuit step, let's go back to that. Let's go back to open circuit step. So let's see. How did I do that? Let's take everything out. So this side is open circuit. This side is open circuit admittance. So this side is open circuit. This is open circuit impedance on this side over here. So it's the open circuit admittance on this side. Admittance, right? Okay. So now, so if I use this point over here, I need negative j 158. So that is right here, right? This point over here. So at this point over here. So now I have to walk. I'm walking towards the generator from the load. So I have to walk from this point all the way here. So look at that. Up to this point is 2.5, right? And this distance is 0.09, right? So my L1 would be here for 2.5 plus 0.09 lambda, and a 0.34 lambda, right? So now L2, if I use this point over here, my value is positive j 1.58. That is, we found it last time, is somewhere here at this point. So 0.6 lambda at that point, right? So that means I have to work from here only 0.6 lambda. So then L2 for open circuit would be 0.16 lambda. All right. So hopefully you understand. You can also use short circuit open circuit step to do the matching, and that depends on where you are, what point are you using, and you have to just work from your open circuit admittance at this point, or short circuit admittance at that point to that point. That's the distance you need for the step. So that means over here, if I use now, this is the load, right? Then if I, at this point, let's say this is for the D1 here, let's say this is the D1 distance, right? If I use the open circuit for at D1, I need 0.34. So this L would be, L1 would be 0.34 lambda. And if I use the L1, that distance D2, if I use distance D2, then let's see, that's a different color. If I use distance D2 over here, right, open circuit, then my length would be 0.16 lambda. So you can use either D1 or D2 distance from the load to match with open circuit, and same thing with the short circuit. All right. So we're going to do this problem in the class. The goal is that you can use a actual component, either capacitor or inductor, or you can use short circuit or open circuit to match with your load, so you can reduce the reflection. All right. There's some applications that you can basically kill your cancer cell using microwave signals, or you can use the high pulse signal to also a high pulse voltage signal to also kill any cancer cell inside human body. And you have seen that this is communication. In communication, what we discuss is basically all our communication. So you can see from satellite to your fiber optics to your even medical application, everywhere you can apply electromagnetic fields theory. That's all. Lecture 10 we're going to spend that lecture only solving the problem. So hopefully we will be ending this chapter at lecture 10. Then you can start chapter 3. All right, and see you for chapter 3.